Thanks for dropping by. We are going to talk about deep generative models today. Before we go into deep generative model, first let me give a brief overview of deep learning. As mentioned in the description of the booklet, deep learning is not suitable for any problem. It is like a mysterious weapon that solves the most complex problems, like killing a dragon. First, deep learning works best when the data size is large. Second, the deep learning combined with generative methods can help discover complex features, especially when there is less domain knowledge. Finally, it has been proven that deep learning works very well on problems like image classification, natural language processing, etc. Deep learning is obviously extremely popular now, that even a movie star will co-author a deep learning paper. But if you look back in the history of neural network, you'll find that it has been there for a long time. For example, the backbone of deep neural network, the backpropagation method, was invented in 1986. The renaissance of the deep learning is due to the more powerful infrastructure we have and the bigger dataset we have nowadays. In fact, the development of the science is like a spiral. Many of the latest deep learning progress origin from a hybrid approach that combines deep learning with traditional methods. For example, the deep reinforcement learning is a hybrid approach that uses deep learning as the estimation model for reinforcement learning. The variational autoencoder is another try to integrate a statistical learning model into deep learning models. Today, we are going to cover one of the main usages of deep learning, deep generative model. Whatever deep generative model you choose, it is an unsupervised model that generates synthetic data that look similar to the input data. After the model is trained, we can either use the left half of the trained network as a feature extractor or the right half of the trained network as a synthetic data generator. There are two types of deep generative models that are extremely interesting. The first one is generalized adversarial networks. Apart from most deep learning approaches that only have one deep neural network, GAN has two deep neural networks, one for generating new synthetic data, and the other one for discriminating which one is real. The benefit of it is that it can generate very realistic data. However, it is very hard to train because we want two neural networks compete with each other. A dynamic balance between two networks needs to be established to train the GAN well. Another problem of GAN is that the latent representation is entangled. A minor shift in latent space might give you something totally unexpected. The second one is variational autoencoder. For variational autoencoder, each latent variable is not one single node. There are two nodes, one for mean and the other for variance. The low dimension representation is sampled from the mean and the variance. The first benefit is that the variational autoencoder has intrinsically disentangled representation. Also, it is easier to train because it only has one neural network. However, it cannot generate as realistic data as a GAN. So is there a method that takes the pros and avoids the cons of both methods? In fact, Recently, researchers start to mix and match two methods to create hybrid approaches that make the synthetic data generated to be both realistic and disentangled. So what's the application of deep generative model? For some image classification problems, when the input image set is not large enough, deep generative models can be used for data augmentation to create more images. Also, for severely underrepresented classes, such as some small cohorts in our acquisition, deep generative model can create more synthetic data to enhance the model estimation. Also, the synthetic data can be used in model selection process to help choose the best model or the best group of models. Here, I give you an example of using variational autoencoder to make people in a photo to smile. We also have a live demo here and you can try by yourself after presentation. As you can see in the video, when I move the mouse to apply a small shift to the values of the latent variables, the person starts to smile. And when I move the mouse back to remove the shift in the latent variables, the smile disappears. We apply similar approaches to the problems inside the SFA. One use case is profile focus. The current method is to do filtering from DU applications. Then Rebecca and Valerie develop an enhanced hybrid method that will be discussed in tomorrow's machine learning presentation. On top of that, we are going to apply variational autoencoder to further improve model performance. It brings two benefits. First, it gives better model estimation for severely underrepresented classes. As you can see from the graph, when the sample size shrinks, the performance of the model on actual data plunges. But with this synthetic data, we can still achieve relatively good model performance. Second, it gives robust estimation of the distribution moments for consistently underrepresented or emerging classes. Okay, that's all for the presentation. Is there any question? Also, we have a mini live demo of using variational autoencoder to make person in the photo smile. Thank you.